Swayam Prabha. Digital India. Educated India.
Privileged to introduce Professor Rameshwar, Assistant Professor in the Department of Electrical Engineering at IIT Madras, as well as alumnus of Affiliation. His research focuses on the fundamental limits of information systems using tools from information theory, coding theory, and applied power. He has also worked on areas such as data privacy, DNA-based data storage, and error correcting tools, contributing to both theoretical understanding and real-world applications. We are truly honored to have him with us today.
Thank you.
Please join me in welcoming Professor Arvind.
Thank you. It's been a long day, so thanks for staying. So we're going to start things off with a little game. Okay. So you can see that I have a collection of caps here. There are 3 red caps, 3 blue caps, unmarked. Okay. So the game is like this. First, I'll set the stage. Then, of course, I'll ask a bunch of you guys to come on as volunteers and try and play this out. Fine. So, in this world, we have n unfortunate prisoners. Okay. N prisoners. N is some integer, okay, positive integer. And these prisoners have this task in front of them. So we lead all these prisoners into one room. Okay. So all of them are put into one room. And the goal is this. These prisoners are very smart, like you guys. So we give them caps to put on. Okay. So we give each of these prisoners a cap, blue or red. Okay. And each prisoner's task is this. So let's organize the prisoners in some kind of circle, okay, so that they can all see each other. So let's call them P1, P2, P3, P4, P7, Pn. Prisoners can all see each other. Each of them has a hat on top. And this hat is either red or blue, only 2 options. Now, based on what the prisoner can see about other people's hats, I want this prisoner, each prisoner, to guess what his or her hat color is. That is the end game.
So, would he know the total number of hats, total red hats and total blue hats?
So, none of that information is provided, only that he can see everybody else's hat. So, strange game, right? But the deal is this, fine? So, we have n prisoners here, and the deal is that each prisoner gets one of 3 options. Either he guesses his hat color as red or blue, or he or she passes. Okay. So by pass, I mean he or she does not hazard any guess whatsoever. So each prisoner has a guess. So let's call the value of the guess of prisoner I as Gi. Okay. So Gi is a guess. This symbol means belongs to. Okay. Gi belongs to red, blue, or pass. Only 3 options. Now the task is this. If ever there is one prisoner who does not pass, okay, so I want at least one prisoner to not pass. At least one guy must make a rightful guess. And suppose that prisoner gets the hat color correct, then all of them are set free. Okay? All of them are set free. Which means that there is some cooperation among prisoners now required, right? So all of them need to come up with a strategy to ensure that they are all set free at the end of the day. That is what we want them to do. But that requires each guy, at least one guy, to not pass, and whoever does not pass must get that hat color correct. So this is the name of the game. So if all of them pass, we fail. All prisoners go back to prison. If one guy does not pass and he gets it wrong, fail. All of them go back to prison. If two guys hazard a guess and both of them are correct, they all go back home safe. You see that? All clear? They go back home. I mean, they go back to prison. So everybody who does not pass must get it right. Everybody who does not pass must get his hat color correct. Just one more complication. So all of them guess at the same time. Okay? Yeah, they all guess at once. It doesn't matter. How does it matter? I mean, they're all put in a circle. They all go home. So whoever does not, so I want everybody who does not pass to get it correct. Yep, except his own. All clear?
So can you discuss beforehand?
You can discuss a strategy beforehand, but you don't know which hat you're going to get. Okay?
So you should tell.
You should tell?
We can't tell. We obviously can't tell everyone what are they, what.
That's not going to help you. I want you to guess your hat color correctly. If you're going to go about guessing other people's hat color, that's a different game. No. Let's play this game. Let's play it and then you can build your intuition. Okay, so I want 3 volunteers. 3 eager guys. 1, 2, and 3. Yeah, please. Got 6 hats. 3 blue, 3 red. So let me just. No. No one can pass also. It's also. Okay, so the game is this. Can you tell people your names, please? Or does everyone know? Sorry? Ananya is here. Then we have Ritvik and Harini. Okay. So I have 6 hats here. 3 red, 3 blue. Okay. So the game is this. No cheating from you guys. Huh? So this is the most important part. I'm going to put this hat on backwards for each of these guys. Okay, so that they can't see the front part of it. Okay. So no cheating and no communicating by other means. So this is the game you need to play. And all of you must guess at the same time. Okay. So in order to guess at the same time, you can write your answer on the board if that's okay for you. Okay. So close your eyes. So, hey, play fair, huh? Close your eyes, man. Can you help? Secure this one. Continue closing your eyes until I tell you to open your eyes. Yeah, please secure the cap that you have on your heads tightly and take a look at the other people's hats. Take a look at the hats. Okay, so they have some idea, okay? No cheating from this end. So now your task is clear. You can keep thinking forever. I have 2 hours in front of me. That will be very, very useful for me. Or you can guess whenever you are ready. No doubts, man. Let's just watch the game. No, you're not helping them. What? Sorry?
Is it the same rules?
I don't get
We
it.
have to, one person can choose pass.
Yeah, you can pass. Let's just watch the game, huh? Let's just watch the game. So you guys can strategize. But you're not allowed to tell each of the other person what his hat color is.
So minimum one person has to choose an answer, then other two can pass, it's fine.
Yeah, it's fine.
Just
Has to be correct. No. Let's just watch the game. We'll take questions later. Please, everyone, just watch the game. Just watch the game.
And my. Wait.
Yeah.
For sure, there are both red and blue.
I don't know. See, I have 3 blue hats, 3 red hats. No, I had some hats are there. You can't see how many. So yeah, okay. Time up, man. Just write or tell me what your. No, all of you must guess at the same time. So pass, red. PSBB students, huh? That's really good. So, shall we do this again? Let's do this again. Get them to be ready. Okay. Okay, we are going to do a retrial while the others think about their best strategy for this game. Yeah, just hold it there. Round 2. Let's see how they fare. You guys can look at each other's hats now. Quickly. Oh man, so this is not fair. They just need to see each other's hats, that's it. This is a math lecture. I don't know about this. Okay, whoever has seen the reflection is not allowed to guess. Okay, if you have seen the reflection, did you see the? Okay, quickly. Yeah. Let's take a guess now, please.
Wait, the same thing that I did last time, is it applicable to our?
No, it's not.
It's not.
Why? I don't think I'm not.
But it probably won't do that.
I think I know what.
I think
I can guess.
I think you're I'm not guessing.
I'm guessing. Okay, I'm guessing blue. Guessing blue.
And you? Yeah, back to jail. Okay, so everybody understands the game.
I thought I didn't.
Thank you.
I mean, I thought that last time since I
And they
did
keep the
that, he
hands.
won't do it again. And he would give like 3 red hats to all 3 of us. So I didn't want to guess.
Okay, yeah. Thanks for your time. Right, so we have an idea about the game. So now the question is, how would you play it if you were playing it? I want to just hear some responses from you before we set about analyzing them. So these hats are random, no? They're uniformly random in some sense. So each person can get either a red or a blue hat uniformly at random. Uniformly at random means? How much is that? 1/2. So each of them has half probability of getting either a red or a blue hat. Okay, it's fair enough. So now what would your strategy be in such a situation? Yes?
So, assuming because we have established that having a red or blue hat is a 50-50 chance.
Yeah.
Let us take, if we having n, let's say infinite, there will be half the number of them would be red, half the number of halves would be blue. So, judging based on how many people, assuming you can look at everybody else, if you can see more red hats than blue hats, then you will assume that you have a blue hat on yourself. Because based on the math, you will prefer the less.
Yeah, this is a very well informed guess, in fact. And good that you're building on the lecture that you saw in the morning. So Keshav, I think, was speaking about how, on average, the probability that you see a certain thing as being head or tail, red or blue, is going to be 1/2. The empirical probability, that is 1/n times summation, whatever you say.
The color of hat you get is based on the person that gives it to you, which means that it need not, the probability that you get a hat is 50-50, but that doesn't mean that the distribution will be 50-50.
Okay, so you're saying that I may only give out red hats.
Yeah, you may be biased in your distribution.
Okay, but assume that, see, as a guesser, you don't have access to this right? You don't have access to this prior information about how I am biasing this distribution. So according to you, each hat is going to be 50% red, 50% blue. So that is the only information that you can work. Your name, please. So Rushil was guessing that, on average, you're going to see half hats as being blue, half hats as being red, if the number of players is large enough, right? So N should be really, really large.
Sir,
Yeah.
so the people wearing red hats would also, every people wearing red hats would see many other people wearing red hats. So they might guess blue. It will be turned out wrong.
It'll turn out.
Turned out wrong.
Yeah, maybe. So you're going against his point. Yeah, so fair enough. So the point is this half behavior, whatever this expectation being half, actually sees certain small fluctuations, right? So Keshav did point out certain things like the standard deviation or the spread of this distribution, which kind of can capture, deviations from the mean, right? You're not going to see exactly one half, you're going to see half plus something. So even if N is sufficiently large, even if the number of players is sufficiently large, you are going to see deviations from this half. So basing it exclusively on half is not a great strategy. Okay, so let us analyze simpler strategies, okay, to begin with. So one of the things that they were doing here was they were designating one player as the guesser. Okay. So they were saying, so this is strategy 1. Strategy 1. So say P1 guesses and P2 all the way up to Pn, well, they just pass. So only P1 guesses and all the other guys pass. Why is this a decent strategy to analyze? Yeah, from this side, yeah. You were saying? Okay. So if there are 2 or more people guessing, if there are many people who are guessing, each of them has a certain chance of getting their hat wrong, right? And so the chance that they all get their hats right is how much? So that is strategy 2. All guess. No one passes. What is the probability that probability that the prisoners go home? Why is it 1/2 to the n? Perfect. So you guys have your calibration done right? So each prisoner has a probability half of guessing his or her hat correctly. If all of them hazard a guess, I want all of them to be right. And that happens with probability half times all the way times half n times, which is 1/2 to the n. So when n is large, this thing is very small. So this is a bad strategy. What about this strategy? What happens here? Only one guy is guessing. Everybody else is passing. So the probability is half. So probability that P1 guesses correctly is the only probability that you need to analyze, which is 1/2. 1/2 is far better than 1/2 to the n, right? For n being larger than 1. Okay, so we have some ideas in mind here. Are there other strategies that you can think of? What about the strategy when each guy, so each GI is going to be uniform in this set GB to pass, GB pass. Sorry, what? RB pass. So each GI is going to be either red or blue or pass uniformly at random. What does uniformly at random mean?
1/3 will guess red, 1/3 will guess.
So with probability 1/3, I'm going to guess red. With probability 1/3, I'm going to guess blue. Probability 1/3, I'm going to pass. How does this strategy fare? Okay, this is not immediately easy. So let's look at the case when n is 3. N is 3, which is the game that we played. What happens here? Not across, so all of them can pass also. Yeah?
So three people, one person, the first person guesses red, then the second person will guess either blue or pass. So then they're wrong. So then the sample says
No. That is not what this means. What this means is that each guy chooses this uniformly at random. They can all take on the same value also. So all of them can guess pass also.
Then what happens if all of them guess pass? What is the
So let's see, let's work things out.
what is the rule of the game for the pass?
No, at least one guy must not pass in order for them to go back home safe. Okay, all of them can't pass and just be happy. Yeah, you still lose. I want at least one guy to not pass, and that at least one guy must get it correct. All those who don't pass must get it right. Okay. Okay, so what is the probability of failure here in the third strategy?
2 by 3.
Let's do it slowly. So why 2 by 3 to the n?
Each event is independent. The probability of failing is 2 by 3 because they only have. Sorry, 1 by 3.
No, that's not what it means. What it means is that each guy chooses independently. Either red or blue or pass. Is that clear? Each guy chooses independent of the other people's actions, either red or blue or pass. So what is the probability that all of them guess red? 1 by 3 raised to the 3. What is the probability that all of them pass? Again 1 by 3 to the 3. What is the probability that one guy guesses red and the other two guys guess blue? Some one guy, not one particular guy.
3. 1 by 9.
Huh? So, what is the probability that one prisoner guesses, so one prisoner passes and two prisoners
So 3C1 into
guess blue?
for one prisoner passes, we have to choose one person. So from this 3 you have to choose one. So 3C1.
3 choose 1. So, once you have chosen this one guy, the other two guys are already chosen. So, you don't need to choose them again.
Divide by 9. Divide by 3 by 3.
Into 1 by 3, into 1 by 3, into 1 by 3. Okay. So 1 by 3 is the probability that this guy passes. 1 by 3 is the probability that this guy guesses blue. 1 by 3 is the probability that the remaining guy guesses blue. Okay, so we have the level, we have the playing field clear. So now what is the probability of failure here? What is the probability that they don't go back home? What are the events that lead to failure in this strategy? Okay, let's enumerate those strategies. Let us enumerate those events. Okay. All pass. What are the other events? These are all exclude. So probability that one passes, only one guy passes, which means two guys guess, and at least one of them gets it wrong. What is this probability? Okay, what is the remaining event? Two pass, one gets it wrong. What is the last event?
One gets it right, 2 are wrong. 2 get it right, 1 is wrong.
No one passes. At least one gets it wrong. A lot of events for failure here. What is the probability of this event? So I'm just seeing how you guys think, okay? I don't want the explicit computation in the end. Power 3. You see that? Each of those guys has to guess pass. Pass. Each happens with probability 1 by 3, 1 by 3 into 1 by 3 into 1 by 3.
We choose one again.
We choose one. by 3.
Previous one into 1 by 3 into
Ah.
155 points.
Ah.
Out of the two, one should differ.
Yes.
That is
Yes.
And into 1 by 3. Yeah, 1 by 3.
1 by 3 into 1 by 3. The other two guys either get it right or get it wrong. Sorry,
So 1 by
that is 1 by 2 into 1 by 2.
1 by 2. So 2 into 1 by 2. So we have already multiplied by 2.
Yeah. Okay, so you can similarly analyze the remaining probabilities here. Okay, I'm not going to do the calculation here. But the big takeaway is, how does this fare against this strategy? Do you have a sense for how well this performs as against this one? This one is better? Why is this better? Point 0.52, where did you go? So we just computed this. No, I have not computed the remaining probabilities, so I have left those as an exercise. Ah, so how much is that? 0.52. How did you get 0.52?
So 1 minus 1 by 3
Hmm.
minus 1 by 9. 1 getting right,
Uh-huh.
2 getting right, and 3 getting right. So 1 by 3 plus 1 by 9 plus 1 by 6. If I subtract it from 1, I will get 2 from 1.
I'm not really sure about that. Okay, so you and I can have a chat later. But really, at least the calibration should be there, right? So this one is going to perform better than this.
Why are there 2 1 by 2s in the wrong calculation? 1 gets it wrong.
So one guy gets it, one guy should get it right and the other guy must get it wrong.
It doesn't matter if the other guy gets it right or wrong. One person gets it wrong, anyway they get it.
Right. So one gets it, but I must multiply by the probability that the other guy gets it wrong. So one guy gets it right, the other guy gets it wrong, right? So what is the probability with which one guy gets it right? What is the probability with which the other guy gets it wrong? That requires to feature in. The multiplication by 2 is the choice of the guy who gets it right. Okay, fine. So let's not worry too much about this computation here, but the point I'm trying to make is that this guy should perform better than this guy. Right? Can everybody see that? Because here at least one guy passes. Right? So whenever a guy passes, he is not going to hazard a guess. Whereas here, there are no passes whatsoever. So everybody has to get it right. Okay, so that is the intuition I want you guys to have in mind. But none of these probabilities look very encouraging. For example, you have half here. You have 1 by 2 to the n, which is particularly small, of success. You have half here. Half is okay, but still not good enough. Here too, if you calculate, this probability also turns out to not be too good. My claim is this. So my main claim is that you can devise a strategy. So there exists a strategy such that probability of success is n by n plus 1. How does n by n plus 1 behave? So when n is very large, almost 1. Very strange, huh? Because I have completely uniform hats. How are these guys even coordinating in order to get their hat being guessed correctly with probability close to 1? So let's think this through. Let's talk about this. So the strategy I have in mind is like this. Oops. So the strategy that I have in mind is that suppose so these 3 prisoners, so take the case when n is 3. These 3 prisoners all have a good look at the other prisoners' hat values, right? So that's all sticky. You want me to write bigger? So consider the case where you have 3 prisoners, P1, P2 and P3. They all have a good look at each other's hats. Okay. So whenever any prisoner sees that the other two hats are the same, then he guesses the opposite color. Sounds strange, no? So does this align with the intuition that if you have, too many hats looking red, you better have a blue, something like that? It is not quite. Okay. So whenever a prisoner sees the other two prisoners having the same hat color, he guesses the opposite hat color. Otherwise, he or she passes. Whenever any prisoner sees the other two prisoners having the same hat color, he or she guesses the opposite hat color. They all guess at the same time, so it doesn't matter.
Two prisoners pass and the other prisoner guesses right, then all three goes.
Sorry, I didn't hear.
If two prisoners pass and the other prisoner gets it right, then do all three go home?
Yes, all three go. So either all three go home or all three go to jail. So if P1 sees that P2 and P3 have the same hat color, say blue, what does P1 guess? If P1 sees P2 and P3 having different hat colors, one guy red, one guy blue, pass. So how does this strategy perform? Okay. So we want to analyze the probability that this strategy results in a success. Okay. So let's do it. Can I take this out?
Sir, but the arrangement of hats on each other set is independent of each other.
So it seems.
So it seems like 1/2 is not changing anything.
We'll see. So the best way to analyze this is to go over all possibilities. Okay. So we have only 3 prisoners here. Can we have everyone's attention, please? Yeah. 3 prisoners here. How many possibilities of hat configurations are there? All red, all blue? How many of those are there? Totally how many? 8 possibilities. So let's write down the 8 possibilities. So I'm going to call 0 as red and 1 as blue going forward. Okay? 0 is red, 1 is blue. So what are the possibilities? What are the possible configurations? Okay. So now the game has reduced to the following. Just find those configurations that are good. Just find those configurations that result in a success. Right? We can enumerate those configurations. No, let's do it one by one. Let's ensure everybody is on the same page. 0, 0, 0, what happens? What does this guy guess? This guy guesses 1. Can you see that? He sees two zeros. He guesses the opposite color. He guesses 1. He gets it wrong. Bad configuration. What happens here? 1, 1, 1. This fellow sees 2 ones. He guesses 0. Wrong. What happens? So now, okay. So we have 2 cases where all hats are the same color. Right? Only 2 situations have all hats being the same color. 0, 0, 0, 1, 1, 1. In all the remaining configurations, 2 hats have one color, another hat is of different color. You see that? Always. 2 hats have one color, another hat has different color. Always, that has to be the case.
Sir, if P1 sees 2 different colors and he passes, then what does P2 and P3 say?
Sorry?
If P1 passes, then what does P2 and P3
it's the same strategy for each guy. So let's go through this, right? So what happens here? So this guy passes, he doesn't guess.
Yes, yes, and right. Yes, and right.
Guess and write. Good configuration. Everybody see that? 0, he sees 0 and 1, two distinct hats. He passes. So he does not guess. So we don't regard his guess at all. What we care about is this fellow's guess. Huh? So he guesses the opposite of the colors that he sees, the common colors that he sees, and that results in a 1 which agrees with his own hat. Interesting. What happens here? Same means what? So this guy does what? Pass. Can you convince yourself that this is true of the remaining configurations? Fancy, huh? So what is the probability that you've got things correct here? What is the probability that people go home safe? Why 6 by 8? 1, 2, 3, 4, 5, 6. 6 good configurations, each having probability 1 by 8. Each of these configurations is probability 1 by 8 of occurring. All with me? Each of these configurations has probability 1 by 8 of occurring. There are 6 good configurations. So 6 by 8 is the probability of success. Just 3 by 4, which kind of agrees with my n by n plus 1. Interesting, but this is not a proof. Okay? This is just an example. So now the question is, can we generalize this? Can we take this to more than 3 players?
Because
Can't take the exact same strategy.
Huh? 2? 2 red and 2 blue may be possible. So a straightforward generalization does not seem to work. We need to add some more masala. So what do we do? Okay, let's look at this example a little more closely. Okay. So you have 8 possible configurations. Which of these are bad? The ones with all of them being the same are bad. Okay. What can you say about the good configurations with respect to the bad configurations? Two of them are the same and the other one is different color. Yes, okay. But with respect to these, so this guy is 110. Okay. This guy is 111. 111 is bad. 110 is not bad.
all 3 is lesser than 3.
101 is good. 111 is bad. So what he's saying, your name again? So what Parthiv is saying is that from a bad configuration, it looks like you can go to a good configuration by flipping 1 bit. Bit means either 0 or 1. You see that? So let's look at this again. So this guy can be obtained from this guy by flipping 1 bit. Which bit is that? The last bit. So you flip this from 0 to 1, you get a bad configuration. Here, you flip the middle bit from 0 to 1, you get this configuration. Here, you flip the first bit and you go here. You see that? So the one interesting observation is that each good configuration is at a distance of 1 from a bad configuration. Can you see that? Distance of 1 means what? I flip just 1 bit in order to go from good configuration to bad configuration or vice versa. I need to flip only 1 bit. All clear or other questions? Each good configuration is at a distance of at most 1 from a bad configuration. It's in fact a distance of exactly 1. Also, no good configuration is at a distance 1 from 2 bad configurations. No good configuration is at a distance of 1 from 2 bad configurations. What does that mean? You can't flip one bit in any given good configuration so that you get either to a good either to one bad configuration or to the other. So let's see this again. Suppose I look at this guy. I flip one bit in order to make him go here. You see that? I flip the first bit. How many bits do I need to flip in order to get him here? 2 bits. I need to flip 2 bits. I cannot flip just one bit and make him go here. So he is at a distance of 1 from this guy. D means distance. And he is at a distance of 2 from this guy. And this is true of every good configuration. Can you see? Every good configuration, for example, this guy is at a distance of 1 from here. You need to flip just this guy. It is at a distance of 2 from here. That is the task that we want to do. Interesting, huh? So this is observation 1. Observation 2 is that no good configuration is at a distance of 1 from 2 bad configurations. Can everybody see what I'm writing? So 2 key observations here. Each good configuration is at a distance of 1 from some bad configuration, and no good configuration is at a distance of 1 from 2 bad configurations. All clear? So with this in mind, can you think about how you would generalize this strategy? I want to do this for really large values of n, while at the same time staying in the binary alphabet. Okay? I want to only work with red and blue hats. I don't want to increase the number of hats.
Sir,
Yeah.
I have an idea, but it doesn't really involve
Mhm.
these two statements. Like, the thing is, if everyone passes,
Mhm.
like, if everyone passes, it means that they've seen that everyone else has the same color cards. So that if everyone immediately passes at the same time, that means everyone will be the same color card. So after everyone says pass at the same time, what if some person immediately says that?
No, you guess only once. You guess only once. You have just one shot. You either all pass and then you can't correct your guess. No. Yes. Speak up, please. I can't hear you. Doesn't look like. So from n people, you want n minus 3 to immediately pass. Okay. But they have more information here. They can see everybody else's. So even there, what is the probability of them getting it? It will be 3 over 4, not n by n plus 1. So you can reduce it to the 3 people case, but you will get a worse probability than what you were scoping for. Okay, let's try to generalize this based on just these 2 observations. Okay. Okay. So this is the question. General n, I have n prisoners, n hats, either red or blue, and I want to get to a success probability of n by n plus 1 using these 2 observations. So what these 2 observations seem to dictate is that they seem to indicate at a choice of good configurations and choice of bad configurations, right? So these are 2 properties that we seem to want to be an invariant across all n. So we call a set of configurations. So how many configurations are there here? General n? 2 power n configurations. So here I was talking about 0, 0, 0, 0, 0, 1 and so on. So here I can talk about n tuples, right? N length binary strings. So this is the set 0, 1 to the n. Have you seen this notation before? It is 0, 1 cross 0, 1 cross 0, 1 all the way cross 0, 1 n times. Cartesian product of 0, 1 n times. That is 0, 1 to the n. So we are working in this space 0, 1 to the n. And the point is we want to designate some set as good and the complement set as bad. Okay. So we call a set of configurations. So let's call this set G of configurations. So G is a subset of 0, 1 to the n, right? You see what this means? G is a collection of configurations. G is a collection of values like 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. It is a collection, it is a set. It is a set that lies inside this set. Why? Because all of them are 3 tuples, all of them are n tuples here. Okay. So we call such a set G as good if properties 1 and 2 are obeyed. Okay. What is the collection of bad configurations here? It's just G complement. Okay. So we call a set G of configurations as good, and correspondingly G complement, which is really 0, 1 to the n cut G, as bad if these two observations hold, observations 1 and 2 hold. Okay. So I call a set of configurations as good if each of them is at a distance 1 from some bad configuration. Each of them is at a distance of 1 from some bad configuration. And no good configuration, that is no element in this set G, is at a distance of 1 from 2 guys in G complement. Guess I'm running out of time, maybe I can continue again. So we'll think about this after a short break.